Welcome to This Explainer. Today, we're diving into a piece of invisible nanotechnology that essentially transforms standard glass into an indestructible shield built for the absolute most extreme environments on Earth. It's called the Nano-Z Glass Shield Extreme GL2. So if you've ever wondered how modern infrastructure survives brutal weather, crazy industrial pollution, and chemical degradation without constantly replacing its optics, well, you're in exactly the right place. Let's get into it.
You know, we all kind of assume standard glass is perfectly smooth, right? But if you look closely, microscopically close, untreated glass is actually this rugged, porous mountain range. It's full of jagged peaks and deep valleys that trap dirt, oils, and minerals. The GL2 treatment, however, completely fills in those valleys. It creates a totally smooth, anti-adhesion surface, which means those environmental contaminants have absolutely nowhere to grip.
Here's a quick roadmap for this explainer. We'll cover 1. Standard glass flaws, 2. Nanotech chemistry, 3. Define the elements, 4. Extreme applications, 5. The 3-step protocol, and 6. Operational value.
Starting with Section 1, Standard Glass Flaws, the Microscopic Mountains. Let's look at the root of the problem and why glass is incredibly vulnerable in extreme conditions. To the naked eye, a glass panel or a camera lens looks perfectly flat. It looks solid. But under a microscope, it's basically a chaotic mountain range. It's an open invitation for moisture, industrial soot, and oily vehicle exhaust to settle deep into those microscopic valleys. And when that moisture freezes, it physically locks into the glass like an anchor. That trapped contamination is actually the starting point for surface corrosion, permanent stains, and what the industry calls glass whitening.
Moving to Section 2, Nanotech chemistry, the Silane Foundation. How exactly do we fix a structural flaw we can't even see?
We have to go down to the nanoscale. The advanced Silane formulation doesn't just sit on top of the glass like a sticker. Instead, this silicon-based foundation builds a complex, three-dimensional, multi-layer cross-link network directly into the substrate itself. It's like completely re-engineering the surface of the glass so it becomes structurally perfect. And the secret sauce here is the covalent bond. We're not talking about a temporary layer of wax or some commercial spray that washes away after a heavy rainstorm. A covalent bond is a permanent molecular lock. It links the GL2 coating to the glass, effectively becoming a part of it. Because of this surface locking, the coating doesn't degrade, it doesn't peel, and it doesn't flake off over time, even under punishing UV radiation. But here is probably the most staggering part. Despite its immense structural strength and complete UV resistance, this entire shield is only 5 to 15 nanometers thick. To put that into perspective for a second, a single strand of human hair is about 80 to 100,000 nanometers thick. Because it operates entirely in the invisible spectrum, you keep 100% optical clarity, zero distortion, zero light reduction, and zero signal disruption for sensitive optics. All right, Section 3, Define the Elements, Physics in Motion. Let's see how this nanoscale chemistry builds into macro-level physical defense. Normally, regular glass suffers from fluid accumulation. That leads to smearing, frost locking, and eventually surface erosion. But with GL2, you get extreme hydrophobicity. It aggressively repels water. You get zero frost locking because ice simply doesn't have any jagged edges to grab onto. Ultimately, the mechanical and chemical endurance goes way up, allowing the glass to shrug off extreme weather and harsh industrial environments without breaking a sweat. This extreme hydrophobicity creates what we call the lotus effect. Water basically forms these perfect little half spheres on the surface. Because the water can't flatten out and grip the glass, it just rolls right off. And as those beads roll, they actively pick up dust, soot, and dirt, basically turning a simple rainstorm into a self-cleaning cycle. Plus, because the surface is totally smooth, any frost or ice that tries to form is instantly blown away by wind or washed off with minimal effort.
That brings us to Section 4, Extreme Applications, from spas to highways. Where is this microscopic shield actually used in the real world?
Well, think about the most unforgiving environments. First, spas and indoor pools. Constant humidity, aggressive chlorine, and sunscreens literally eat away at standard glass, causing that opaque whitening effect. GL2 blocks that completely. Next, traffic and security cameras. These sensors have to stay perfectly clear, but they are constantly blasted by industrial pollution. And finally, transport infrastructure. Highway signs, mirrors, toll sensors, they are relentlessly coated in oily vehicle soot, environmental salinity, and dust. The coating actively repels these exact contaminants. Now for Section 5. The 3-step protocol: preparation and application. You can't just casually spray this on. Let's look at the rigorous protocol required to bond it.
This requires strict professional discipline. Step 1 is preparation, a deep chemical clean. You have to use a specialized Z200 solution to strip all existing oils. And here's the catch: you can only use fresh white paper. Reusable cloth fibers leave behind microscopic grease that ruins the bond. After that, a microclean with a CW101 solution. Step 2 is coating. You spray a fine mist and spread it gently in circular motions using a paper-wrapped sponge, working in small half-square-meter sections at a time, and no mechanical pressure. Step 3 is polishing. You wait 15 to 25 minutes for the particles to link up, then polish it with clean paper until you hit 100% optical clarity.
Once that manual work is done, the chemistry basically takes the wheel. At T0, the exact moment polishing ends, the unseen chemical action continues. Over the next 2 to 3 hours, the surface hits initial activation, and that water and dirt repellency kicks in. But it takes a full 24 hours at room temperature for the Crosslink network to hit 100% curing. Once you hit that 24-hour mark, maximum durability and complete chemical resistance are locked in permanently. Finally, Section 6, operational value, the macro-micro loop. Let's step back from the nanoscale and explore the real economic impact for operators. The bottom line here is massive operational efficiency, because this shield can be applied on-site, directly onto existing client infrastructure, without dismantling expensive camera systems or shipping glass panels to a factory. The initial savings are huge, but the long-term value is even better. It drastically slashes manual cleaning frequency. You don't need harsh, expensive chemical cleaners anymore. A simple damp wipe is usually enough. That extends the life of the equipment, preserves clarity, and totally reshapes maintenance budgets. Backing all that up are some incredibly solid technical specs. It has a density of roughly 0.97 grams per cubic centimeter and a highly stable neutral pH between 7.0 and 8.0. It's built on an ethanol base, meaning its boiling point sits right between 78 and 100 degrees Celsius, allowing for perfectly controlled evaporation during curing. And maybe most importantly for operational safety, once it's applied and dried, is classified strictly as non-hazardous to health. So I want to leave you with this final thought. Knowing what we know now, having looked through the microscope at that porous, vulnerable mountain range that makes up standard glass, can any modern, expensive infrastructure truly afford to remain completely unprotected? Is leaving high-end optics and architectural glass totally naked to the elements a risk you can really afford? Thank you so much for joining me for this explainer, and remember to keep questioning what you can't see with the naked eye.